We're going to finish up this week talking about one other phenomenon that occurs in the presence of thermal energy, and that is the energy or the expansion of an object when it is heated. And here are two examples of the effect of heat and the expansion that occurs with heat. On the left, you have what's put into a road to take this into account. These are joints that are put into a road, especially in a bridge. You'll see these, so that when the road heats up, it's allowed to expand and it doesn't crack the road or the bridge. On the right, you see the effect of heat on the viscosity of a liquid. Now, the change in length is equal to the original length times a factor known as alpha, which is the linear thermal expansion constant or coefficient, and it differs for different substances, times the change in temperature. So let's do a calculation to see how this happens. If you have a copper bar that is 11.54 meters in length at 20 degrees, how long will it be at 95 degrees? If the coefficient of linear expansion is 17 times 10 to the minus 6. Well, we just had the formula here. We said that the change in length is going to equal the original length times alpha times the change in temperature, which in this case is going to be 11.54 times alpha, which was 17 times 10 to the minus 6, times the change in temperature, which goes from 20 to 95, so 75 degrees, and it's going to get longer. And if you do this calculation, delta L will be some number, and this is going to be 1.154 times 10 to the 1, and this will be 7.5 times 10 to the 1. And so you have approximately 10 to the minus 4, and you multiply these three actually. If you multiply these three numbers together, you'll end up with some number which will be in meters. And obviously, it's not going to change the length a great deal, but it will change the length. And if you had a situation where this rod or bar was in a tight space, it could warp, or it could cause cracking or whatever. Here's another situation. This is an unknown bar. It measures exactly 9 feet at 30 degrees. What is the coefficient of expansion if its length at 110 degrees is that length? Now, this coefficient expansion is immune, or it doesn't have units, and so except for the temperature, because the length cancels each other out. And so delta L is equal to L alpha delta T. If you solve this for alpha, you're going to get delta L divided by L delta T, in which case delta L here was 0.003, L was 9, and delta T was from 30 to 110, so that's 80 degrees. So if you do the math here, you'll get alpha per degree centigrade. This change in length can be used in various ways, and this is called a bimetal strip. You can see, and bimetal strips are created using two different metals, and the two different metals purposely have different coefficients, alpha coefficients, so that one changes in length more than the other. And so, for example, in this example, you see that when the two are together, the two strips are the same length. And when cooling would occur, or heating, either one, let's say that it's being heated, the bottom strip will get longer than the top strip, and that will cause it to bend up and break the contact. So this is one way of a device known as a thermostat, and it's a device that regulates temperature. So that you could imagine that the top is when the thermostat is cool, and as the room heats up, the bottom situation occurs, breaking the connection and turning off the heater. And the bimetallic strip, as I said, is the strip made of two different metals that will accomplish this. Now we're going to talk about the different ways in which heat is transferred. Heat can be transferred generally three ways, and all three ways are shown in this diagram. The first is by direct contact, and that's called conduction. The second is through an intermediary or a medium, and that's such as air or water, and that's called convection. And then the third is directly by radiant energy, and that's called radiation. So conduction is the thermal energy transfer from the hotter object to a cooler object through direct contact. And what occurs is that the molecules of the hotter object strike the molecules in the cooler object and impart energy to those molecules, and thus increasing their kinetic energy, and it warms up. The conductor is a substance that will allow such a flow of heat energy, and an insulator is a material that resists such thermal flow. You saw in the previous diagram that the poker for the fire was being held by a pair of mittens, and those mittens are made of materials that resist thermal energy transfer. A pot holder is made of a material that resists thermal energy transfer. The second is convection. Convection is thermal energy transfer from one place to another by a medium, which can be a fluid or a liquid. And you have natural convection that occurs due to gravity. This is the situation where hot fluids or hot air rises and cold fluids or cold air sinks, which is why the higher parts of a room will be warmer than the lower parts of a room. You can also take advantage of this by circulating the air through the room, blowing hot air out the bottom, and it will circulate to the top and cause a circular motion, which will help transfer the heat throughout the room. You've also heard of a convection oven. A convection oven is just an oven with a fan, and the fan circulates the air to allow the heat energy to be transferred throughout the oven more efficiently. Now, the movement of the fluid or the air is called a convection current, and you've seen pictures of this probably in various movies where the air above a hot concrete will shimmy or move, and those are convection currents off the hot asphalt. Radiation is the last, and it's thermal energy transferred by electromagnetic radiation. Heat is a form of electromagnetic radiation. It's in the infrared band, and it will move by just as light moves or UV radiation moves. Now this is called a Dewar's flask, and a Dewar's flask is created in such a way as to use all three means of movement of heat to prevent the loss of heat or the gain of heat. If this is a cold, you want to prevent the heat coming in, and if it's a hot liquid, you want to hold the heat in. First of all, the inside of the flask is coated with a reflective material, and this reflects the infrared radiation back inside the flask. Then you see that there's a space between the inner bottle and the outer bottle. This space is evacuated. The space prevents contact, so there is no conduction, and the space also has a vacuum which prevents convection by eliminating the medium. So all three of these are taken into account in the creation of this Dewar flask. Now, here is a situation where we use both convection, primarily convection, to transfer energy, heat energy throughout a house. And what you do is, on the left here, you have an oven or a heater or a stove where you're burning gas or wood, and then this heats air that surrounds the stove, and this heated air then moves up the by natural convection up into the upper part of the house, and then the colder air at the same time comes back down into the lower part of the house and is sucked into the furnace or into the heater or into the stove and is reheated, and then it moves back up in a circular motion, and you can see this on the right.